Okay, so let me start this lecture. Briefly review what we did in previous lecture. In the previous lecture, I explained about the domain dynamics in a polar coordinate system. So as you see here, we have two kinds of domain walls. One is the perpendicular case and the planar anisotropic case. And also the domain wall, we have two kinds of domain walls. One is the blow type, the other one is Neal type. And the domain wall structure we can obtain by the variational principles in this form. And the domain wall width, delta, which one is very important length scale in domain wall dynamics, is determined by the ratio of the exchange stiffness and anisotropy. In the denominator, this is the initial anisotropy constant, and this term came from the demarcation energy, or in other words, shape anisotropy energy. And also it depends on the details of the domain wall structure and the Dirac coefficient over your cells. And please keep in mind we are working in a polar coordinate system here. And we calculate the torque for each component R, theta, and phi. And R component of torque is not important because this torque is always parallel to the magnetization. So that means they are not acting on a motion of the magnetization. And we also need this two matrix form. Actually, this is transform matrix from the XYG to the R theta phi, or from R theta phi to the XYG. And here is the example. In a precession torque, we can calculate M cross H, and M is the R vector. So we have to calculate R cross G using this matrix. And as a result, we have a phi component only. So we can write down the torque, basis of the R theta phi coordinate systems. Then we can calculate also damping torque, and we have also a theta and phi component here using this relation. And also we can calculate the Dirac torque by the demarcation field, which one is determined by Dirac coefficient or Dirac tensor with the magnetization. In last class, I made some mistake in this representation. I missed this term. So I correct one. So anyway, if you start from here, you can do by yourself. It's not that complicated mathematics. It's very simple matrix operation, just with some simple relation of the trigonometric functions. And then with the R cross product, we have a zero component in R and theta and phi here. Okay. And finally, we can obtain the total torque. This is precessional term. This is the damping term. This is the Dirac term. And we can convert this torque equation to the theta dot and phi dot here with this relation. Okay, and this is the first of the differential equation for theta and phi, and we have a phi dot here and theta dot here. So those two equations are coupled one. Okay. So let's try to solve the equations. In a steady domain motion, that means, as we already mentioned several times, the domain motion, we have a two regime. One is called the steady regime, the other one is precession regime. Yeah, we already explained the creep regimes, but creep region is we consider a lot of defect. But in this model, in this domain dynamics model, we simply ignore that kind of defect. Actually, we can include that effect of defect by introducing the barrier potentials, but in this case, in this derivation, we didn't think about that kind of a defect. Okay, so what's the meaning of the what is the meaning of this steady domain motion? As I already said, in an external field, domain velocity, we have a kind of motion, and here, in this region, what happens is the angle, the assumption angle phi is constant, or in other words, the dot, phi dot is 0. Then, yeah, phi dot is 0, so we have this equation is 0. And also we think about that the center of the domain wall. At the center of the domain wall, theta is phi over 2. So from here to here, we have a domain wall. And at the center of domain wall, theta is always pi over 2 for nil and the Bloch wall in both cases. So to find this is zero condition with the theta is pi over 2, this term, the Dmax term is disappeared. Only we remain these terms. And you can find this relation. So in this relation, we can easily find theta dot is alpha gamma h0. And let's compare to these two equations. So that means theta dot, you can replace theta dot with this one and this relation. That means for a given field H0, the angle phi should satisfy this relation. Okay. And this one is nothing else but half sine 2 phi. So we can rewrite this relation. Okay. And the domain velocity can be obtained by this relation. This is actually no. The theta dot means the direction of the magnetization from the z-axis. The magnetization is changing to this direction. Ratio is theta dot. So that is this theta dot is related to the velocity of the domain wall, and okay, so this is the magnetization, and this is theta, and this projection is sine theta. Okay, and the theta dot is something like this. So the velocity of the domain wall is given by let's see, yeah, relation. So in the center of the domain wall, theta is pi over 2, so we can simply sine theta is 1. So domain velocity is determined by theta dot, which one is given by here. So we can obtain this relation. Okay. So as we already mentioned, the velocity of the domain wall should determined by the time scale and the length scale, because the velocity is the length divided by time, or length multiplied frequency. And this gamma is 0, give us some kind of frequency term in your given system. And delta is the length scale of the domain wall dynamics. So it should be given by delta gamma H0. And also, the damping alpha play a role, as we explained. The alpha determined how the magnetization aligns to the field direction, how fast. If alpha is large, then the magnetization is aligned to the field direction more fast. Alpha is small, then it takes longer. So anyway, finally, we can obtain this relation. And here is one thing we have to think about that. This steady motion is always valid. Okay, let's think about this equation. This is sine to phi means it should be the absolute value of this one should be less than 1 here. So that implies if H0 is smaller than this one, this steady condition is valid. But if H0 is larger than this one, there's no phi satisfy this condition. So that's what we define this kind of H is called HW, or Walker breakdown field. Walker breakdown. So this steady motion is valid only when the H is smaller than HW. And how it can be big? Actually, this term gives us order of 1 Tesla. The typical ferromagnetic material, the mu0 ms is order of 1 Tesla. But the Nx and Y is generally very small. In films, Nx and Y is almost 0. And in a wire, if we actually we are playing with wire for the domain wall devices. So in this case also, Ng is always about 1. But Nx and Y is almost 0. But fortunately, Ny is slightly larger than Nx in this case. So we have a certain value, but it's very small value. Generally, HW is very small. So that means this this field is usually very small. So we can observe this steady domain motion within very small field region. Okay. And the domain velocity is given by this form. Not for only blower, it's also valid in a nil domain, sorry. And we already obtained the domain velocity in a steady motion. We have this result. Okay, so let's think about this precession motion. This precession motion implies the angle phi is not constant anymore. So actually, in this case, we have finite phi. That means it's not 0, means phi is always changed. So actually, this one is a kind of increasing function. So that means the magnetization, the angle of the sine angle of the domain wall is rotating. So what we have to do is taking the time average. So let's take the time average of the theta dot. And in this relation, we can take in the time average for the phi dot and this term. And also phi dot and theta dot here and time average of this term. But as we already said, phi is changed from 0 to large number. So this term gives us average value is 0. And also, we think about the theta is pi over 2. So those term is going to 0. So we can obtain this simple form. Because we can drop this term, these two terms. We have this one. And we have a time average of theta dot, and we can obtain the velocity, time average of the velocity, and it should be delta over sine theta and theta dot. Okay, we have this one. And if you're using this relation, theta dot is the alpha sine theta phi dot. We can say, we can replace with this relation. And we can insert to here, phi dot is the dominant velocity divided by alpha delta. Okay, we have this relation. And here, theta dot, we can replace by dominant velocity again here. And we are also working on theta is pi over 2. So sine theta is just 1. So, okay, we can rearrange this relation. We can move on this one to the left-hand side, and we can collect the alpha in this form. We are here. So finally, we obtained the relation of the domain velocity of the precession region. We have here. So compared to this relation, the difference is the role of the alpha here. Generally, alpha is small value. So this term, sorry, so alpha is denominator. This term gives just alpha. So in a precession region, alpha velocity is given by this form. Sorry, this is a steady motion, and precession motion, we have this form. So H0 is the applied field, but in this case, it should be smaller than HW. So, as we already mentioned in last class, gamma H0 gives us order of gigahertz. But in a small field, this frequency is small. Actually, this one, for the one rather large field, we have order of 10 gigahertz. And delta is order of 10 nanometer. So, as we already mentioned, this term gives us order of 100 meter per sec. But we have alpha here, so it gives us order of meter per sec. But in this case, alpha is in a denominator. So inverse of alpha give us 100, and but delta H0, the H0 is quite small, so we have let's say smaller than gigahertz. So this term give us order of 10, 1 or 10 meter per second. But we have alpha, 1 over alpha here, so we can obtain the relatively fast velocity here. But if we applied moderate field, we cannot observe this steady motion. Usually we obtain only precession motion. Okay. So let's solve the equation of motion of domain 1 again with full terms. Now theta dot phi dot, we have this relation. And the domain 1 velocity is given by the time derivative of the position. The q is the position vector. And this q, the q dot is related to theta dot with this relation. We assumed the sine theta is 1 by setting the pi. Theta is pi over 2. Okay, so we using the pi over 2 for all thetas, we can simplify this equation in this matrix form. Here, we have a theta dot phi dot here. We can make such kind of matrix equation. Okay, and also we can introduce the domain 1 anisotropy, which one is mainly came from the shape anisotropy of the domain 1, the Dirac field. And so they have a m square term and the dimension coefficient term. Introducing this k domain 1, this term you can rewrite with k domain 1. Okay. And this matrix term we may rewrite by taking the delta to here, because q dot is the dimension of the meter per sec, the velocity. But if we divide by delta, they give a 1 over sec unit. So it's the same to the phi dot unit. So this it's kind of frequency domain, frequency dimension. And we can move this matrix to right hand side by taking the inverse matrix, and you can obtain this term. And we may ignore this term for the for future simplification, because alpha is usually small. So anyway, so we can rewrite this result to here. We can obtain q dot phi dot for the general case. Okay. So if we think about the steady state, phi dot is 0. So that means this is 0. So they should satisfy this relation. And in this case, we have a q dot in this form. It's the same result in the previous case. So now we understand how domain 1 behave under external magnetic field. Do you have any question about this derivation? I hope this mathematics is not that difficult for you guys. Everyone okay? Theta is the just radian, so theta dot should be 1 over time, 1 over sec. Is it clear for you? Theta is the dimension is radian. So theta dot is d theta dt. So it gives us just 1 over sec unit. V is the meter per sec. So here, for example, here, delta gives us the length scale, the meter. So this gives a meter, and theta gives us 1 sec. So it is the meter per sec. Are you okay? Good. So far, we talking about the field-driven domain motion. But as you see here, if we apply the field, the parallel domain is getting larger, and the opposite domain is getting is shrink down. So actually, we want to make a device, domainal device, by moving the domainal in the same direction. So by the field-driven domainal motion, this domain will be disappeared, and this is not what we want. So that's why people are excited with the spin transfer torque instead of the field. We can move domain very easily with the field, but it's not useful for the device. So let's think about the spin transfer torque at the domain 1. As you see in this cartoon, domain 1 is the continuous rotation of the margination. And if you think about just a single surface, then actually it's exactly same to the spin transfer torque in a NTJ or GMR structure. We have a two ferromaterial layer. Okay, so let's think about just the two layers. And one layer margination is here, the other one is here. There are small differences. So this is the what we learned in a previous lecture for the STT M structure. We have a spin torque term here. And here, M polarizer means the magnetization direction of the previous layer. And this is the switching layer magnetization. So you can replace this M polarizer is to the M I-1 layer. Yeah, we have now think about the I layer. So we can just replace this term to here. And the remaining problem is we can rewrite this cross product with this relation. Here, this Mi-1 means the other word. This is the magnetization at position of the here dx means the one lattice parameter. So we can taking the Taylor series in this form. And actually the dx is nothing else but the lattice parameter with the minus sign. Plus. So we have a minus sign here. Okay. And this term will be disappeared by the vector product of the the other MI. So the remaining part is here. So this torque acting on the domain wall is given by the derivative of the magnetization. So that means if the magnetization is continuous in a domain, inside of the domain, this torque is 0. But if we have a special variation of the magnetization, means it's non-collinear and means there is some domain structure, then it's non-zero. Okay, so let's put this one to replace here. But please remember that the df is the thickness of the ferromagnetic layer. But in this case, we are talking about just the single layer. So dl, df are the same. So they will be cancelled out each other. So we can rewrite the domain torque by the domain wall here. And here Bj is the unit of the velocity, and it's given by this form. And here I introduced the non-adiabatic spin torque. Sometimes we call this is beta, or sometimes we call this eta. So what's the meaning of the non-adiabatic term? Actually, when we are talking about the STT in our MLAM, we said if you have a free layer here, and if there is an incoming magnetic moment or incoming spin, there's some exchange coupling, so they are the outgoing term is just parallel free layer. So that means there is a very, very strong exchange coupling, and it takes a very short time to align this free electron to the local spins. But the electron is moving fast, and the coupling strength is not infinitely strong. So that means the outgoing electron spin is not exactly parallel to this localized spin. There is a small difference, let's say. And this small mismatch gives us some kind of additional torque. And this additional torque should be proportional to this direction. So actually, this is a local spin, this is an ingoing spin or outgoing spin. Then we calculate the spin transfer torque between them. So this torque is belong to this plane, in this screen plane. And this local spin, somehow we can apply torque to this local spin. Then this torque should be 3 component. They can be 3 component, and 2 of them should be belong to this plane. But one is this direction, and the other one is parallel to original spins. And then the remaining part should be perpendicular to this plane. That's what we call the non-adiabatic torque. This same thing happens to in the domain wall. So the direction of the domain, the non-adiabatic torque should be this form, because this torque must be perpendicular to this torque. This adiabatic torque, this if we have A cross B cross C, it gives us B cross. this relation. So that means this vector is a linear combination of the C and B vector, right? So that means they are perpendicular to the A vector. Yeah, because we have a B cross C is one vector and A is another vector. The result vector should be perpendicular to A and B cross C, right? It's the same. So here, this torque is perpendicular to the M and M cross the derivative of the M. So we should find some direction to the perpendicular to these guys. So they should be this one. And also this torque should be perpendicular to the M. Okay. Yeah, they should be perpendicular to these two vectors. So we can define the direction of the non-algebraic torque in this form. And the magnitude of the Cj, we believe that is the proportional to the spin adiabatic spin torque, and we define some coefficient, proportional coefficient beta. So this term usually very small, but sometimes it can be not that small. So in that case, the non-adiabatic torque plays very important role. Okay. And please keep in mind the unit of this Bj and Cj are meter per sec, the unit of the velocity. Okay, if you have any question, please interrupt me. It's not easy part, so understand anything, please double check it. Everybody okay? Good. So let's do it, the equation again. So far, what we did is this part. And now we are doing same thing. We try to find the total of these two terms. Okay, so first let's think about the adiabatic torque. Yeah, here we have a m cross round m round y. Here in this equation, I took the x to the y direction or current directions, but in our previous coordinate system, the current is following to the y-axis. So I replace the derivative to the y-axis. Okay, and we can took the vacuum rule again here. We have a m dot m, and we have this term. And this gives us ms squared. So this term, the first term, is very clear. And the second term is actually 0 because yeah, this term and this term are perpendicular because the m is here and dm dy should be perpendicular. So this is 0. Okay. And here, if you're taking the derivative to the y to the m, we can rewrite this form by the chain rule. We can find the round m, round zeta, and round zeta, round y. And round zeta, round y give us sine zeta delta. And this one, m vector is ms and r hat. So we have a r hat, round r hat, round zeta. And round r hat, round zeta is here. And we have a zeta hat. So we can replace this is zeta hat. So finally, we can obtain the adiabatic spin transport torque in this form. Okay. And now we have to find the non-adiabatic torque. The non-adiabatic torque is just m cross round m round y, and we already found this one is zeta hat, this one is proportional r hat. And the cross product of r cross zeta gives us phi. So finally, we can obtain torque equation by the spin torque in this form. Yeah, this term is what we previously ordered. So let's think about that. Zeta is pi over 2 and introduce the domain 1 anisotropy energy again. We can rewrite the whole equation in this simple form here. Or if you take in the inverse matrix form, you can obtain this relation. Okay. So this is two terms, all of the spin transfer torque. If we didn't apply the field, this term is dropped. Only these two terms working as a driving force of the domain work. Here, one thing is, this term is generally very small. Alpha is small and beta is also small. And this is the order of 1. And this term is also order of alpha. So compare this term and this term, which one is more important? This term is seems like very important. Okay, but actually, you know, okay. Anyway, so let's do it. Let's try to solve it. Yeah, let's think about the zero field case. And for the simplicity, we think about the zero non-adiabatic contribution. then above equation is even simpler. So in this case, when Bj satisfied this relation, this term is going to 0, right? So we have a y that is 0. But in this case, this term are exactly the same. So equal to 0. So that means if we applied a small current, actually the Bj is proportional to the current density. So Bj starting from 0 to certain value, they always satisfy this relation by adjusting angle phi. So domain 1 doesn't move. So that's what we call the intrinsic pinning field. This HK should be this kind of intrinsic pinning of the domain 1 with the spin tensor torque. That's the different point. In a field, they cannot make this term 0 simultaneously because of the role of alpha. But in a spin transfer torque, those terms can be 0 together. So that's the different point in a spin transfer torque driven domain motion, the field driven. So that means we need at least certain amount of the current density to move the domain wall to overcome this intrinsic pinning. But if we introduce the non-adiabatic torque, non-zero beta, we can rewrite the equation in this form. Okay, so that means if we satisfy this is 0, then we can find the q dot by substituting this relation to here. And after we rearrange this relation, we can obtain this term. Okay, let's compare to the field case. In field case, we have a gamma is 0 of the frequency and multiply delta, we can obtain some velocity. And the ratio, the rho of alpha is in a denominator. And here, the Bj is velocity, unit of the velocity by the current. And the domain wall velocity is determined by mainly Bj, but the ratio of beta over alpha. So in this case, beta is 0, we can obtain q dot is 0. So without non-adiabaticity, the domain wall doesn't move in this condition. Well, it is valid only when in this equation we have this relation. And it should be less than 1 because it's the sign. So when Bj is smaller than this one, domain wall velocity is determined by this relation, and they have a steady state motion. And if beta is 0, we have this relationship. So anyway, if Bj or the driving current is smaller than certain value, domain wall has a intrinsic pinning if we don't care about the non-adiabaticity. But with the non-RDF ST, domain 1 can move. And let's think of the precession motion. Okay. Actually, in a domain 1 motion by the current, they show very similar behavior to the field-driven one. We have such kind of work breakdown and steady motion, work breakdown, and then steady motion, the precession motion. Okay, so let's think about the large STT. Means we have a large current density overcome this limitation. Then we can take the time average again and Q dot and time average of the phi dot. And this term is going out by the time average. It's going to 0. And the remaining part is here. Okay. Only this term is survived. Okay. Oh, it should be time average to here. Yeah, this term is coming here. And here we can ignore the alpha square, and alpha and beta, two terms are small, so we can ignore this term also. So that means the velocity of the domain wall is proportional to the BJ itself. Actually, this is the also velocity unit. Okay. And the domain wall velocity in a field is given by this form. Okay. And as we already calculated several times, this can be order of a meter per sec when alpha is 0.01. In a steady state, velocity is given by this form. And this is the precession term. The question is, beta over alpha is getting larger than 1 or smaller than 1. That's the question. Alpha is usually small value and beta is also small, but beta depends on the materials, and the determination of the beta term is very difficult. It's not a well-defined constant, actually. Okay, so let's back to the definition of the beta here. The BJ. BJ is this term, and let's ignore these non-adiabatic terms. And just taking the unit, the J is the current density and is given by charge carrier density and charge E and the electron velocity, electron drift velocity here. And mu zero EMS is not that important. So actually, this term is proportional to the drift velocity. So Bj is actually proportional to the domain the electron drift velocity. Let's think about that. Radius is 1 millimeter copper wire. Which one is the typical wire we are using in our everyday life? Okay. And let's think about just 1 ampere of current. If you have some extension in your home, multi-tap extension, we have a rather thick wire here. And there are several ones. So typically this kind of multi-tap, maximum allowed current is order of 10 ampere. 10 ampere is quite large current in practice. So anyway, let's calculate this one. The current density is given by 1 ampere divided by R square. So we have a 10 to minus 6, means 10 to 6 ampere per meter square, and it should be NeVd. And the velocity of the derivative velocity of the electron can be calculated easily by this relation. Charge carrier density in a kappa is order of 10 to 29 meter per the cube. So we can obtain 10 to minus 5 meter per sec. So the derivative velocity of this current is very slow. It's very, very slow. But don't confuse, this is the derivative velocity. The real electron velocity is determined, the Fermi velocity is order of 10 to 5 to 6 meter per sec. But this derivative velocity is the average velocity of the domain, the electrons. With this Fermi velocity, the electron moving randomly in any directions. So in a zero applied current, this average value is 0. But with applied certain voltage, there is some small motion of the average, motion of the average of this Fermi velocity, and as a result, all electron moving to specific direction very, very slowly. That's the meaning of the derivative velocity. So actually, when we're talking about the domain-wide motion here, the electron passing through this direction and this direction are cancelled out each other. Only the net motion of the electron determined by this derivative velocity give a net contribution. So anyway, so actually this motion is quite slow. But if we're increasing the current density to the 10 to 12, that means we can multiply. Now we are 10 to 60 here. So we can multiply the million number to here. We can obtain 100 meter per sec. We can obtain that. So let's think about that domain wall device. If we have a single bit stored some information, length scale of 100 nanometer. And if you want to read or write this bit, it should be moving certain distance, at least 100 nanometer again. So that should be happens order of sec. So that means we need the domain velocity order of meter per sec, 100 meter per sec.